So far in our unit on rates of reaction, we have reacted two chemicals, A and B. It's irrelevant of what the chemicals are. Manipulated one variable known as concentration, first off, and the results showed that as the concentration increased, so did the rates of reaction. In other words, it was faster. Then the next day, we manipulated the same two chemicals, A and B, and tested it with various temperature changes. So overall in the classroom, we divided the temperatures up and the results showed as well. As we increased the temperature, we also increased the rate of reaction. Reaction occurred quicker than in cold temperatures. So today what we're going to do is manipulate another variable by adding a catalyst into the picture. So what we're going to use is hydrogen peroxide at two different concentrations. First off, we're going to use 3% hydrogen peroxide, which can be found over the counter in any type of store. We're going to add it with no catalyst at all and see what our results are. And then we're going to take the same 3% hydrogen peroxide and decompose it and actually use a catalyst. And in our case, we are going to use potassium iodine as our catalyst and see what will occur. Then the next test, we'll use a 30% hydrogen peroxide, which we're increasing then the concentration. We're going to first test it with no catalyst at all. And then the second time around, we're going to add potassium iodine, which is our catalyst. Remember that a catalyst isn't affected. However, it does speed up the reaction. So what actually occurs and how does it speed up the reaction? Well, we can take a look at our kinetic energy curve and draw that out. So we're going to find our results. We found that with using our 3% hydrogen peroxide no catalyst, really, we didn't have time to see it react. Nothing really occurred. However, when we added the potassium iodide to it, we did see that it did bubble up a little bit and there was some reaction. So we next took, let's say, a graph of concentration this way. So I'm going to say that 3% concentration here. We're going to also increase the concentration. So if these represent the number of particles on this axis, we're going to increase that concentration. We're going to show the graph looking something like this, and we're now going to put 30% concentration. All right, so we have 3% and 30%. On the bottom, I'm going to use our kinetic energy, and I'm just going to show that it increases going this way. So this graph is great. It shows us that there is an increase in concentration. However, we also need to add the fact that now we are going to add a catalyst when we had none to start with for both of the concentrations. And to do so, we need to add our progress reaction. So looking above here, we're going to utilize this little graph. So if we're looking at this reaction, of course, ours was a decomposition of H2O2, and we're looking at a double replacement in this reaction. But needless to say, we're looking at the activation energy, which is at this point right here. If we're taking the difference of activation energy from here to here, when the reaction occurs, we're getting 100 minus 40, which will give us 60 kilojoules. That's how much energy it took for the reaction to occur. So we can take that and put the values down here. Let's start with 10, make this match, 20, 30, 40, 50, 60. I'll extend that curve a little bit, so the line there so you can take a look at it. So looking back up, we'll notice we'll take and we'll mark the 60 mark for our activation energy. I will mark it up right here. And this then can be explained using this kinetic energy and our activation energies up here. This is how much of the reactants reacted with 3%. We added a 30%. We're looking at this entire part of the graph would have been represented by what was reacted. Now let's say a catalyst came into the picture. Catalyst actually increases the rate of reaction by decreasing this activation energy. So it's taking a new path. So let's say the new path leads us to this. It's still going to have the same reactants and same products, but now we are looking at a different activation energy. So now we're going from 40 to just 60 kilojoules. So if we subtract those two, we get a 20 kilojoule difference. So now taking that information with the new activation energy with the catalyst, we're at 20. So I'm going to mark that activation energy. I'm going to mark it with a catalyst. I might as well mark this without. And then looking at the graph itself, now this is represented, this area right here is represented where the 3% concentration reacted. And look at the difference with the new activation energy of 20 kilojoules, how much more reacted with the 30%. So there we have it. With a catalyst, we did increase the rate of reaction, and we can graphically depict this.